Okay, so good evening, everyone, and welcome back to this series titled as All About Neutrinos, online interactive lecture series for general audience, which, as you know, are being organized by India-based Neutrino Observatory, the INO project, for many months now. Of course, there has been some gap in the last couple of 2-3 weeks, which was interrupted because of by the high energy physics symposium that was held in Bhubaneswar, Mysore, and also the next week being the important astronomically important day on 21st, and because of that we had to again defer it. And today we have here with us Professor Sujan Sengupta from Indian Institute of Astrophysics, Bengaluru. He's going to talk today on extraterrestrial life, the most elusive customer. So it's going to be very interesting talk, especially to the younger member of the audience. But of course, it will also cover many interesting science and astronomy for every one of us. I'll take a couple of minutes to formally introduce today's speaker. Professor Sengupta is a professor at the IIA, a premier research institute, of course, of the country in Bengaluru, under the Ministry of Science and Technology, Government of India. After completing post-graduation in mathematics from Burdwan University in West Bengal, in 1990, he joined Indian Institute of Astrophysics, that is IIA, as a CSIR research fellow, and he obtained his PhD degree from the Department of Physics, Bengaluru University in 1996 on astrophysics. After a brief period of postdoctoral research at Vanderbilt University, Nashville in USA, with a NASA fellowship, he returned to India and joined IIA as a faculty in 2002. His research activities mainly include theory and observation of extrasolar planets, brown dwarfs, neutron stars, and low mass binary stars, and so on. Currently, he is in fact only scientist in India to work on extrasolar planets. He pioneered the polarimetric method for detection and characterization of exoplanets and brown dwarfs. Professor Sengupta was one of the signatories, along with the late Stephen Hawking, Professor Frank Drake, and Professor Kipton et al. Of the Breakthrough Initiative project established by Yuri Milner, the search for extraterrestrial intelligence. Currently, he actually collaborates with scientists of NASA's Ames Research Center, Jet Propulsion Laboratory, and Caltech. He also collaborates with the principal investigator of European Science Space Agency's upcoming space mission Ariel, and with the scientist of University College London. So he's a member of the International Astronomical Union. Besides publishing several research papers in the top-notch international peer-reviewed journals, Professor Sengupta has also authored a popular book entitled Worlds Beyond Our Own, The Search for Habitable Planets, which was published by Springer International. So with those few words of introduction about today's speaker, I now invite Professor Sujan Sengupta to give his lecture. Thank you very much.
Good evening, everybody. I'm sure that all of you have heard about alien life, about extraterrestrial intelligent life, but those are confined in science fiction movies, serial, etc., etc. Today, I am going to tell you the real systematic and scientific search for life beyond our own world, that is called extraterrestrial life. Thank you, Dr. Satyanarayana, for your kind invitation and the kind introduction on behalf of India-based Neutrino Observatory. It's a great pleasure for me to be here and to talk with the students and the faculties. Now, we know one planet very well. That is the third planet of a most ordinary star called Sun. But the greatness of this planet is that this is so far the only known planet which is habitating or which is habitable. Now, about 5,000 years ago, the Sumerian thought that their culture, their art, their technology all were taught to them by some extraterrestrial intelligence, which was amphibian in nature. And they didn't consider it as a god or goddess, but they just considered some super intelligent people from outside the earth. At the same time, the Babylonian thought that those moving lights in the sky, now known as planets, are the residents of the god and goddess. The Greek thought that the moon is a place where the departed soul lives. So, therefore, this imagination or this speculation of life beyond the solar system or beyond the earth is quite ancient. But then, about 350 years before Jesus was born, the Greek philosopher Aristotle came up with his idea that the earth is the center of the world, and the sun and the stars and the planets all are orbiting the earth. And because of that idea, the plurality was completely lost. Then after 100 years after Jesus was born, Ptolemy also supported this idea, and as a consequence, the Catholic Church made a dictate that nobody should oppose this idea that Earth is a special place and it is the center of the universe. So for the next 2000 years, we believe that we live in a world where Earth is the center. But then when more and more observation started coming, more people started observing the sky, then people got doubt that there is must be something wrong. Then in 1500, a Polish astronomer Johannes Kepler, he gave a theory that the world is actually heliocentric. It is not geocentric. So all the objects, including the Earth, is orbiting around the sun and not around the Earth. But at that time, because of people were afraid of the chart, nobody could come up to support his idea except the astronomer or that time the philosopher Giordano Bruno. But Bruno was then burned alive because he was supporting Copernicus' idea and opposing the Aristotelian philosophy. But then as time passes, how more and more observation has come, and the Tycho Brahe has collected a large amount of data on the movement of the celestial objects. And based on that data, he actually came into a compromising theory. What he told that let us assume that, or let us have a model where all the planets and the stars are actually orbiting the sun, but the sun itself is orbiting the moon, the earth. And therefore, the earth-centric concept written, but it has become a new kind of compromise between an earth-centric and a heliocentric world. But as more and more observation comes and the motion of the celestial object was determined, Kepler came into the laws of the motion of all these planetary objects, and this was quite apparent that geocentric world doesn't work. And so it was established that we live in a system, a planetary system where sun is the center of the earth. In the meantime, Galileo discovered the satellites of the Jupiter. He also saw the ring of the Saturn, which was finally discovered by Huygens. Huygens also discovered the satellite of the Saturn and the ring of the Saturn. But at that time, nobody considered, or nobody thought about planet outside the solar system or life outside the solar system. In fact, Giordano Bruno, he thought that, he first pointed out that if sun is a star, then all the lights, the millions and billions of light in the night skies are also like our sun. And if that is the case, then they too have planets like our sun has the planet and planetary system. And if they too have planets and planetary system, then there must be quite a few planets which are very similar to Earth. And if that is the case, if there are quite a few planets which is very similar to the Earth, then there must be some life elsewhere. So that was the first consideration of life outside, scientific consideration of life beyond the earth. Then subsequently, Sir Isaac Newton also pointed out the similarities in the various planetary system in his book Principia. But the final scientific, the first scientific report that appeared from Madras Observatory by the then director of this observatory, Captain William Stephen Jacob, in the year 1855. The Madras Observatory was established by British East India Company in 1786 for meteorological purposes, but it was used subsequently by for observing stars. They have only 6 to 8 inch telescope, and they used to take the motion or the position of the star through the photographic plate. So in 1855, Captain Jacob reported in monthly notice of Royal Astronomical Society that a binary system, a binary star 70 OPOC, it is not following Kepler's law. So there is an anomaly in their motion. And he proposed that if there is a Jupiter-sized planet in this system, then that can account the deviation of the motion of the two stars in 70 OPOC from the Kepler's law. So at that time, the other observer from Chicago University, she immediately supported this idea. But then in 1899, there was a theoretical work that such type of system may not be stable. But people didn't rule it out. Later on, it was when more sophisticated telescope and more better instrument appeared, it was found that Jacob actually did some error. At that time, there was no computer, no calculator, nothing was there. So he excluded the effect of Earth, and because of the effect of Earth, his calculation on the motion was wrong. But it is still considered now as the first false alarm for extrasolar planet. So there was then the effort continues. The effort continues after that also. In 1943, D. Rayl and E. Homeward, they again reconfirmed a Jupiter-sized planet around 70 OPOC that Captain Jacob reported. In 1944, Strand reported the discovery of a planet around 61 Cygnus star. In 1944, Peter Van de Kamp claimed a planet around the Barnard star. This Peter Van de Kamp worked for several decades to search for extrasolar planet, but these are all by astrometric method, by monitoring the position of the star in photographic plate. At that time, photographic plate was also not very improved and the telescope was very small. In 1963, after almost 2 decades, the same person, Peter Van de Kamp, claimed one more planet around Barnard star. And then, so 2 planets around Barnard star was reported. In 1973, the report for a decade-old 340 decade result was published, and 12 several planet was claimed. But later on, it was found that all were false alarm. None of them are planet. In 1984, Branford A. Smith and Richard G. Taylor, they discovered a circumstellar or a circumplanetary disk around Beta Pictoris star. And that is the first time some planetary type of object was discovered. Although this is not a planet, but this is related to the formation of the planet. Finally, a true alarm came from an unexpected host, but not before another round of false alarm. So in 1991, Biles and A.J. Line and Seward, they claim to have discovered a planet around a neutron star, PSR 1829-10. But in 1992, next year, they withdraw their claim that there is no planet found. Now, this neutron star is not actually the proper is a proper star. It is a dead body of a star, as you know that when a massive star they get exhausted of their nuclear fuel, they start expanding and they become a red giant, and then they start collapsing. So if the mass of the star, the initial mass of the star is more than Chandrasekhar limit, that is 1.4 mass, then the star explodes into supernova. And after the explosion, the remnant that acts as a object called the neutron star. The neutron star has a very strong magnetic field, and therefore it radiates in a very narrow collimated beam of light, mostly in radio. And this rotating neutron star is called a pulsar, which is popularly known as the lighthouse of the universe. So, so these two planets, the planets that is reported was around one of the pulsar. Then in 1992, Ulsjeong and D. Frail has reported discovery of a planetary system around a millisecond pulsar PSR B1257 plus 12 by using the Arecibo radio telescope. So millisecond pulsars, the pulsar, but which periods are very short. In 1 millisecond, they give their orbit. So a planetary system, and actually two planets are discovered around such type of pulsar. Then in the next year, he not only confirmed, after 2 years, he not only confirmed his claim the previous years, but he also reported one more planet, that is the third planet in the same system. But getting this planetary system around a neutron star was a very rare incident. So at that time, nobody believed it, because people was in doubt that how after the new supernova explosion, a planetary system would survive. So some people speculated that during the supernova explosion, after the explosion took place, then the debris the planet might have formed. But then there was not much planet or planetary system discovered around pulsar. Finally, in 1995, Michel Mayor of the Geneva Observatory reported the first planet orbiting around a sun type of star, 51 Pegasi b. So in 1995, Michel Mayor and his student at that time, PhD student Didier Couillot, they developed a very sophisticated spectrography instrument called LOD, through which they checked as at least 142 star, and they discovered and confirmed a planet, a Jupiter-sized planet. Actually, it is slightly bigger than Jupiter, around the star 51 Pegasi, and this is known as 51 Pegasi b. And because of this discovery 25 years ago, they were awarded the Nobel Prize in Physics last year. Now, if you see this 51 Pegasi, it's very nearby star, so it is a very bright star. And here the 51 Pegasi, but you know that the planet, they don't have their own light, and they are, even if they are bright enough by their by the reflection of light from their star, they are hidden from the intense brightness of the star. So therefore, it is not possible to directly observe a planet or directly see a planet and discover it. So the astronomers take indirect method. They determine the effect on the star by the planet, and thus they confirm the presence of the planet. So there are quite a few methods through which the astronomers confirm the presence of a planet. The method that is used by Michel and Didier is called the radial velocity method, or the Doppler method, which was proposed by Otto Struve in October 1952. And what is this method? Now, we know that when two celestial objects of same mass orbit each other, they don't orbit around the center of any specific object. They orbit around the center joining the line of their centers. So this is called the barycenter. So this middle plus line is the center of rotation of these two objects. Now, if one object becomes heavier, if one object is heavier, then this barycenter moves towards this heavier object. So now if there is a planet orbiting around a star, then this barycenter goes inside the star. So it is not exactly the center of the star, but it is inside the star, the barycenter, around which both the planet and the star orbit. So now if you watch this system, if you observe this system edge on, then you can see that there is a wobble in the star because of the presence of this planet. Now we know that our sun our Jupiter imparts a radial velocity 12.4 meter per second on the sun, and the Earth also imparts a tiny radial velocity 10 centimeter per second to the sun. So now note that this theoretical method was proposed in 1952, but it was applied successfully and discovered in 1995. So in science, it works like that. The theorist goes sometime much faster than the experimentalist or the observer. Now, the problem remains the how to detect this ubul, this tiny ubul, 10.4 meter per second or 10 centimeter per second. So what astronomers do that? They pass the starlight through an instrument called spectrograph. So when they pass this radiation through spectrograph, the light of the star gets splitted into different color associated with the wavelength of the light. Now in this spectrum, you can see there are some black, dark vertical lines. So these vertical lines are caused because the light from the star get absorbed by the atoms in their atmosphere. And that causes these absorption lines. So but when the star is fixed, it is a stationary, it doesn't move, then these lines have a particular position, a fixed position corresponding to the wavelength associated. But when the star moves towards you, then this wavelength gets shifted to the blue region, and therefore there is a movement in the dark line also. And when the star moves away from you, there is a red shift, and this is called the Doppler shift. So when a object moves to a light source moves towards you, the light get blue shifted. If it moves away from you, the light get red shifted. Now by fixing a particular absorption line, namely a iodine line or an organ line, the astronomers determine the radial velocity of the star, and from the radial velocity they calculate the period of the planet and also the projected mass of the planet, and they confirm the presence of the planet around the star. Now in 1997, after 2 years of the discovery of the first exoplanet around a solar type of star 51 Pegasi b, 3 new 51 Pegasi type of planet was discovered by an American group led by R.P. Butler. And then in 1999, the first planetary system, a multiple planet around Andromeda, the HR 458, was discovered by the same American group. At that time, very few astronomy group has such type of sophisticated instrument that could measure such a tiny displacement in the absorption line by removing the motion due to Earth, by vibration, by Earth, the air pollution, everything. So this two group started working, and they discovered the first few planets by using this type of special instrument. Now, after 5 years, another method was used, which was also proposed by same Otto Stube in the same paper of the same journal, and and that is called the transit method. Now, what is this transit method? So when a planet passes through the star, that is when it transits across the disk of the star and in front of the observer, then it blocks certain amount of light from the star. As a consequence, the brightness of the star reduces systematically or periodically. So when the planet passes across the disk of the star, there is a systematic decrease in the brightness of the star, and from monitoring this periodic decrease in the brightness of the star, astronomer confirm the presence of a planet around that star. Now, if there is more than one planet, then more than one times the brightness will reduce, and therefore this light curve, that is the curve expressing the decrease in the brightness, get modulated, and one can find out how many planets are there, their exact period. In fact, from this method, the exact size of the planet can also be found out, which cannot be found out by the radial velocity method. Radial velocity method, however, can give the projected mass, but transit method can also give the inclination angle of the planet. And therefore, by combining these two methods, one can find out the exact mass of the planet, its radius, and therefore the mean density, and therefore the surface gravity of the planet. The first transiting planet was discovered in 2000 by two groups, and they published their result in the same journal of the same volume, one by one. So this object is called HD 209458, and it is detected by the same group of Barclay group. One is the below the number 2 is the Harvard group. So by using the observatory, the telescope available, I started this work a bit late after I returned from USA. I joined IIA in 2000, but then it took some time for me to settle and to do all those things. But we had at that time only one telescope, that is the Himalayan Chandra telescope. This telescope, the J.C. Bhattacharjee telescope, was installed much later. And so by using these two telescopes, the Himalayan Chandra telescope at the Indian Astronomical Observatory in Hanle, in the Ladakh region in the Kashmir Union Territory, and by using the Jagadish Chandra Bhattacharjee telescope, which is a 1 meter class, 1.3 meter class telescope at the Vainubappu Observatory in Kavalur in Tamil Nadu, we also we also monitor the transiting planets, and we have also detected quite a few star like that. Here at the light curve, you can see these red vertical lines are the observed brightness of the star, and there is a clear fall when the planet transit across the star, and when we model it, we can precisely find out the period, the size, the mass, and everything. And this observation is taken from J.C. Bhattacharjee telescope at Kavalur. This is much more accurate. And here, and so far we have done follow-up by using transit photometry with the use of the Indian facility of as many as 10 planets already discovered, but our result is so accurate that it is now considered as the default value by NASA Exoplanet Science Institute in NASA Exoplanet Archive. So these are considered by NASA and EOSO as the best result about the properties of these planets. And we are continuing following up to improve the parameters of this planet. At the same time, we are also searching for new planet, and this observation will continue as long as possible. Now, coming back to HD 209458b, or it is popularly known as Osiris, the first discovered transiting planet. This planet is first in many aspects. So the first atmosphere has been detected from this planet in 2002 by the Harvard group. The first infrared emission was also detected from this planet in 2005. And then the first molecule, the water vapor, is also discovered from this planet at the same time to another transiting planet, HD 189733b. Anyway, by the time before the first planet 51 Pegasi b was discovered, we know there was 9 planet in the solar system. We didn't know any planet beyond the solar system. But in 2006, the International Astronomical Union, that is the parliament or the senate of the astronomers worldwide, has resolved that Pluto is not a planet, and therefore the number of solar planets reduced to 8. And this decision was delivered after a marathon discussion, deliberation, everything. And this was mainly prompted by the discovery of several planets which are much larger than Jupiter and much heavier than Jupiter. So now at that time, only the ground-based telescope was used. And so the range of our search was limited to only 300 light years around the sun. But as more and more planet outside the solar system was getting discovered, then NASA stepped into the picture. So it consider launching a space telescope, a dedicated space telescope to search for planet outside the solar system. So in 2009, NASA launched
10,
the
9,
KEPLER space telescope
8,
into
7,
the space.
6, 5, 4, 3, 2. It's engine start. 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
Burning our engine chamber pressures are building. Groundless solid motors are building chamber pressure.
Now, as soon as Kepler was launched and Kepler was functional, the range of our search increased by 10 times, but in a narrow region. So now we could search around 3,000 light years from the sun. And then as the data started coming from Kepler, we discovered such a huge number of planets with such a different varieties of planets that our concept on planets and planetary system got completely revolutionized. We knew the largest planet so far as Jupiter, but now we found planets which are 2 times, which are double in size than Jupiter and which are 10 times heavier than Jupiter. We know Jupiter is a cool star, is an icy gas giant, but we discovered planets, Jupiter size of planet, which are very near to their star and therefore they are very hot, so hot that even iron can melt, even gold can melt. We have discovered planets which are intermediate between a gaseous planet and a rocky planet. These are called mini Neptune, and that type of planet is not there in our solar system. We discovered planets which are slightly bigger than Earth, and we call it super Earth. We discovered planet around double star, that is called circumbinary star. That is planet has 2 parents, and their day and night, their temperature all are determined not by 1 parents or 1 star, by 2 stars. There are several kind of planet, cool planet, warm planet, hot planet, roasted planet, all are discovered. In the meantime, some planets are directly imaged by the space-bound telescope Hubble and the Spitzer, and the ground-based telescope Gemini and VLT. So what it was done that the starlight has been blocked by an instrument called coronagraph, and then the planet was imaged. So here there are 2 planets. Here this is a peculiar object. This is the planetary mass object, but this is a failed star. This is called brown dwarf. I'm not going in details about that. This is also another interesting object which is intermediate to the least massive star and most massive planet. It has born like a star, but it has failed to become a star because of the lack of sufficient mass to ignite helium. And here you can see a direct image of a planetary system where 1, 2, 3, 4 planets we can clearly see. And here is another planet, Beta Pictoris, for which this protoplanetary disk was discovered long ago. The planet was discovered now. Now, why this could be imaged? Because these planetary systems are very young. They are about 100 million years old, and therefore they are still contracting, and therefore they are so hot that they are still emitting infrared emission, and that infrared emission can be detected from our telescope. Now, at the same time, some planet has been discovered which has no star, so they are rogue planet or planet without any parents. So in 2013 Pan-STARRS telescope, it discovered quite a few free-floating planet around nearby, around in our neighborhood and around our solar neighborhood. Now the question remains that, okay, these are all giant planet, gaseous planet, free-floating planet, but where are the planets that could be habitable, that could have life on it? Because ultimately that is the goal, that is the main goal, that is the main aim of the astronomer, to detect the life somewhere else, to answer the eternal question, if anybody out there or if we are alone. So now for that, we need to search for a region of a star that is called the Circumstellar Habitable Zone. So the Circumstellar Habitable Zone was first used, the term, by Su Wang in Astronomical Society of Pacific long ago. So by definition, circumstellar habitable zone means the region around a star where the temperature will be such that water can exist in liquid state. So quite naturally, the distance of this habitable zone depends on how bright or how hot is the star. So it is defined by the luminosity or the brightness of the star. So now, if suppose some extraterrestrial intelligent life is searching, they are also very curious to know if they are alone in their system or life exists elsewhere in our galaxy. And they are much advanced in their technology, with their computer, in their telescope. So they discovered sun, and they discovered all the 8 planets of the solar system. So now how they will find out that the Earth is habitable or life may exist on Earth. So what they will see that they will, if they consider only the brightness of the sun, they will find that all the 3 planets, that is Venus, Earth, and Mars, are habitable. That means they have sufficient temperature for water to exist in liquid form. But all the planets has some property which is called the reflecting property of albedo. That is, a certain portion of the starlight received gets reflected out to the space. So Earth reflects 30% of the sunlight to the space. Mars reflects 20% of the starlight to the or the sunlight to the space, and Venus reflects a whooping 70% of sunlight to the space. And therefore, if one considers this albedo or the reflectivity, then this extraterrestrial intelligence will find that none of these planets in the solar system are habitable, or they have the condition for life to survive, because the habitable zone has to be shifted much near to the star in order for them to become sufficiently warm, if we consider the albedo. But we know that the Earth is habitable. We know that, in fact, on Earth, water can exist in all the 3 forms, liquid, solid, and gaseous form. So what the extraterrestrial intelligence will miss? So what they will miss is called the greenhouse effect. Now, when the sunlight enters to the atmosphere and it hits the surface, the solid surface or the rock, it heats up the surface, and then it starts going back to the space. But while after hitting up the surface and when it gets re-radiated, it becomes weaker. Its energy becomes much less, and its wavelength shifted to the infrared region. So this infrared radiation, when it travels towards through the atmosphere, it gets scattered by the molecules like carbon dioxide, water, nitrogen, etc. several times. And so many times this infrared radiation gets scattered that they cannot escape the atmosphere of the Earth. As a consequence, they are trapped in the Earth atmosphere, and they warm up the atmosphere of the Earth. So if this greenhouse effect was not there, the temperature, the mean temperature of the Earth would have been minus 15 degrees Celsius. And because of this greenhouse effect, the ambient temperature of Earth atmosphere increased by 30 degrees Celsius, and it becomes 15 degrees Celsius, thus making Earth as the habitable planet in the solar system. So quite naturally, Hubble also started searching for such type of planet which are in the habitable zone of other star, and very soon it has discovered a system, KEPLER 22, and where they found that it found that KEPLER 22b is in the habitable zone of its star KEPLER 22. But then it was found that this planet is actually much bigger than the Earth. It is actually the size of our Neptune, and therefore it cannot be a rocky planet. It may be an entirely gaseous planet. Now here is another problem, that not only the environment has to be appropriate for water to exist in liquid form, the planets need to have a rocky surface or a solid surface to retain the water. We know that in the solar system, all the outer planets like Jupiter, Saturn, Uranus, Neptune, all are made of fully gas. So it's if somebody drops you over Jupiter, you will just go down, flow with the gas. Everything is gas unless and until your density becomes less than the density of the gas inside. So it was found that this planet is actually gaseous planet. So even if it is in a habitable zone, it may not be a habitable planet. Now, after a few years, Kepler discovered another planet around Kepler 69. Here they found out a planet which is slightly bigger than Earth in the habitable zone of Kepler 69. But again, it was not beyond the debate that this is so big that it may be a mini Neptune instead of a Earth or a super Earth. Subsequently, Kepler 62 system was discovered. These are several planets, and out of that one planet, two planets was in the habitable zone of their star, and they are of the very similar size of Earth, slightly bigger than Earth. These are called the super Earth. In 2017, a colony of rocky planet is discovered around by using the ground-based telescope TRAPPIST, and this is called TRAPPIST-1. So out of the 7 rocky planets, 3 planets in these systems are in the habitable zone of this star. Then, after again just 2 years ago, another Kepler planet was discovered, which is the planet is of exactly same size of Earth, and it is in the habitable zone. But the problem is here that all these stars, the host stars, are the faintest star. They are much cooler and much fainter than our sun, and therefore their habitable zone are much nearer to their star than the Earth is around the sun. And as a consequence, these planets are exposed to the intense activities, intense ultraviolet rays and the charged particle of their star. These are called M dwarf, and usually it is known that the M dwarf has a very strong magnetic field of about 1,000 times more stronger, 1,000 times stronger than the magnetic field of the sun, and therefore they are quite active, and therefore all the time flares and charged particles are coming out from them, and so it is very doubtful that a planet in the habitable zone where the temperature is appropriate for water to stay in liquid form can have really water on them, because water may evaporate because of this charged particle thing. So finally, very recently, Kepler 452 system has been discovered, and that is just like a solar system. Yes, silent is. 452 has been discovered, which is very similar to our solar system, and the planet is also very similar to the Earth. Now the question is that if we discovered the planets, there are quite a few planets has been discovered which are in the habitable zone of their star and which are rocky, but is that sufficient for life to exist there? Is this two condition that a rocky planet in the habitable zone of a star can really harbor life on it? Then we go to face another difficult, another challenging question: what is life? Now, by life, we know only those species, only those phenomena which we see on the Earth, because so far we have not seen any form of life or any living or any similar thing anywhere outside the Earth. Now, which thing we will call as life? Unfortunately, there is no fundamental definition of life. So suppose 400 years ago, if somebody would have asked you what is water, you could have taken a description for water, that water is a liquid, it's a colorless, it's a waterless, odorless, it flows from top to bottom like that. But a description can never provide the complete picture of some substance. Somebody may come with a beaker of methyl alcohol and tell that, look, this is also liquid, this is also colorless, odorless, this also flows from top to bottom. So what is the difference? So description can never tell the specific properties, all the properties, and it always remain debatable. Now, if somebody asks you that what is water, even a school child can also tell, oh, water is a molecule made by 2 atoms of hydrogen and 1 atom of oxygen. Now, from that very fundamental formula, from that very fundamental definition H2O, one can derive all the properties, physical and chemical properties of water. Unfortunately, such type of definition of life doesn't exist because life is a system. Nevertheless, NASA has given a working definition of life, which says that life is a self-sustaining chemical system capable of Darwinian evolution. But it doesn't say really anything in the sense of practical. So what type of chemical, what type of substance we'll consider, and how we will make that realize that it is self-sustaining or it is not self-sustaining. Now, if we extend this thing to our Earth-based life, then we can say that life is an ensemble of organic material governed by a self-sustaining synchronized system of chemical process and characterized by, this is very important, characterized by metabolism, replication, and evolution through natural selection. Now, what is this organic materials? Organic materials are based on carbon molecules, and they combine with hydrogen, oxygen, or nitrogen and form a big chain, and that is called the carbonic material, organic material. And that's why Earth-based life, we call it carbon-based. It is carbon-rich. Now, by synchronized system of chemical processes, the hormone, enzyme, those commands and control our a living body. The metabolism. Metabolism is a process through which the cell extracts energy. So the oxygen is carried by the blood. Now, when the blood is supplied to the cell, this oxygen oxidizes the food stored in the cell, thus producing the energy. So when the oxygen supply is stopped, the cell cannot produce the energy, and we can tell that this is a dead. Therefore, metabolism defines the dead. Metabolism also defines the growth of a body. Now, what is replication? Replication is a property of a gene, is a function of gene through which it copies exactly another cell from one cell, and it transfers the property of one species to the next generation. So that is called replication. And the evolution through natural selection is the response of a species to the nature. So because of the evolution through natural selection, we know that if someday we can find out a cat or a dog on Mars, we can tell that there are many more dog and cat, and there are many other simpler species on Mars. If we do not find out any other species, then we can tell that this cat and dog is imported from elsewhere. So because of the evolution through natural selection, we know that in Earth, complex life has evolved or come from the simplest form of organic material. Now the question will come, somebody may ask that, how do you know that outside Earth life may not be made of, life will be made of carbon only? Why it cannot be oxygen, iron? Why not it be by aluminum? Why not it by silicon? Well, now we know that the laws of physics are same everywhere. When you throw an apple here, it will go and it will come, it will fall to you by following the Newton's law. Now the same Newton's law is valid at the remotest corner of the universe. The same Maxwell law, the same Faraday law, the same Einstein law, we work exactly in all over the universe. So the laws of physics are unique. It is universal. So now at the basic level, the biology, the lot of biochemistry is also the basis of the chemistry, and the chemistry at the basic level is the functioning, is the properties of the electron. So there is no reason to believe that the bioscience, the biochemistry will be different at different places of this universe. And again, the nature has considered the most optimal condition for the origin of life, in the sense that carbon is the fourth most abundant element in the universe after hydrogen, helium, and oxygen. And carbon has a property that it can easily combine with various elements to form various kind of other molecules. And therefore, carbon is has a advantage over making a long chain and over making several type of elements. It is solvent to water like that. But still, if for the sake of debate, somebody tell that life may exist in other form, in other materials with different biochemistry, then there will be no way for us to recognize that form as a life unless and until it is an intelligent life that inform us that it is also a life but made of different element and different biology. In that case only we can say that the laws of biology differs from place to place. Otherwise, there is no reason to believe that the laws of biology is different at different place. Now, when I tell about intelligent life, then again we are facing another debate that what do we mean by intelligent life? We know that the human is the most intelligent species in our galaxy at least. But somebody in our planet on Earth, somebody may tell that my pet dog is also very intelligent, it listens to me. Somebody may tell that, okay, chimpanzees, gorillas, monkeys, they are also intelligent. Dolphins are also intelligent. But how we, the astronomer, will define intelligent life? Now, we define intelligent life when a species has the capacity to receive, to generate, and to transmit artificial electromagnetic wave, that is the radio wave. So, otherwise, other intelligent life cannot get us. They cannot see us. We cannot communicate with us. Now, so we call a life as intelligent when the civilization advance at that stage at which we can receive, we can generate, and we can transmit artificial electromagnetic wave, namely radio wave, to prove our intelligence, to prove our existence through intelligent mode. Now, in that way, we have discovered radio receiving, transmitting, or generating process just about 150 years ago. So during that 150 years ago, that radio wave has traveled from us, those artificial radio wave, just 150 light years away. But our galaxy, from the center to one edge, is about 50,000 light years away. So where we are situated, the sun is situated from there, the nearest edge of the galaxy is 20,000 light years away. So if from the edge of the galaxy, if some intelligent life sends some radio signal, it will take 20,000 years for us to receive it. So that is the problem. By that time, that civilization may get destroyed, that civilization may leave our galaxy, or anything can happen. Now, here, since I am giving a talk for the India-based neutrino observatory, I must point out something very new which many of you may not have heard, and even I have not told it before in any talk, that so far we think that the radio wave could be the mode of communication by intelligent life, and therefore we are using all type of radio telescope to find out artificial signal. But a civilization much advanced than us may also use a collimated neutrino beam as a mode for communication. That is because neutrino travels almost at the same speed of light. It doesn't interact with the ordinary material. But the advantage is that it can be distinguished from the natural neutrino sources very easily, from the background very easily. So if an advanced civilization, much advanced than us, can produce by a multi-TeV muon collider a collimated beam of neutrino, then at least our neutrino observatory in ice cube experiment, or even the Indian neutrino observatory, can very easily detect it. So therefore, this is a new area that the neutrino detector can also serve for the search of intelligent life if they are actually communicating, they are using neutrino instead of radio wave to communicate with us. There is already there are some proposal, there are some calculation on that, but these are all speculation for that. So far, we have not received any signal, any signature, any artificial signal from the space, but the possibility remains. And if we really want to search for that, for intelligent life, we need to also think of other method, and the Neutrino Observatory is one of the observatory that may open the new possibility in case an intelligent life is communicating by using high energy. Somebody tell that, okay, that will take, that neutrino collider will take huge amount of energy. Now remember that according to the Cartesian scale, we are zero civilization. That means we have not even met our energy requirement by nuclear fusion. We are still using fossil. So we are civilization zero. Now the type 1 civilization will be those civilization which will meet their energy requirement entirely by nuclear fusion. The type 2 civilization, they will meet their energy requirement by entirely by their star. And the type 3 civilization, they will need the energy from the entire galaxy. So the civilization scale is defined in that way. So maybe a type 2 civilization will be much easier for them to communicate through neutrino instead of the old radio wave or the radio communication. Anyway, so the thing is that we cannot search for life. We cannot go to that planet. We cannot see that whether the atmosphere is sufficient. The only thing we will know about a planet that it has an appropriate temperature for water to exist in liquid form, and it is rocky. But there are several conditions that makes life to origin, to life to survive, and life to evolve. So those are the properties that we can never make out by sitting from Earth. So what we will do, how we will search for life, we'll search for biosignature from those planets. Now we know that if you take the spectrum of our 3 planets, that is Venus, Earth, and Mars. So in their spectrum taken by Spitzer Space Telescope, which is the infrared telescope which has just got retired, so there are plenty of signature of carbon dioxide in all the 3 planets. But in addition to the carbon dioxide, the Earth shows the signature of water and liquid water, ocean signature, and it shows oxygen molecule. Now here, these oxygen molecules serve as a biosignature, as a bioindicator, because free oxygen was not available at the time Earth was born. So after all the atomic oxygen was combined with carbon, nitrogen, and hydrogen to form carbon dioxide, water, etc., etc., there was no free oxygen molecule. About 3.9 billion years ago, a bacteria called cyanobacteria, they started doing photosynthesis, and through photosynthesis, they started emitting oxygen molecule. At the same time, volcanoes and plate tectonic also emitted some amount of oxygen molecules in the atmosphere. And as soon as the cyanobacteria started doing photosynthesis, the chemistry of the Earth atmosphere, the chemical composition of Earth atmosphere got completely changed. And only those species which could tolerate oxygen survived, and those for those species for which oxygen was poisonous called completely extinct. Now these oxygen molecules, when it reaches the troposphere, where the ion in the top of the atmosphere, it get hits by it get dissociated by the ultraviolet radiation of the sun, and it becomes atomic oxygen. Now one atom of oxygen and one molecule of oxygen combines to form a molecule that is called ozone. And on Earth atmosphere, we know there is a ozone layer which is protecting us from the energetic ultraviolet ray from the sun. So oxygen molecule, ozone molecule, at the same time, when the living species dies, the production of methane methane can be also produced by chemical process, but methane in an oxygen-rich atmosphere is not possible unless and until there is a equilibrium, non-equilibrium, and that non-equilibrium is maintained by living species. There are phosphine. You know that few months ago there was a sensation that phosphine is detected in the atmosphere of Venus. So we will look for such type of molecular signature. And how we will search for such type of signature? Because the planets are hidden over the star, no, we will take something called the transmission spectra. So when the planet transit across the star, its opaque area blocks the starlight. But the thin atmosphere of the planet through which the starlight, a part of the tiny fraction of the starlight passes through the atmosphere of the planet and it interact with the matter present in that atmosphere. And then when we take the spectrum of a star which is transiting during the transit of a planet, and when the planet is not transiting and we subtract it, we can find out the various molecules and the atoms present in the planetary atmosphere. And this is called the transmission spectroscopy. So we have numerically simulated the detail of the this transmission spectroscopy. At present, the transmission spectrum of a few giant gaseous planets are also available, and we compare our numerical model with that. And here are some models, and the red lines here are the observed, the detected transmission spectra in different wavelength, and blue line is our theoretical model. We have also compared with the upcoming JWSSB simulated model with that, and so far our numerical code is the most sophisticated, the state-of-the-art numerical code. And in future, when more space telescope will go, we'll be able to model those transmission spectra and to analyze the transmission spectra to tell that what type of molecule is there, and this will lead us to the discovery of biosignature or biomolecule. Now at present, I will just skip it because we need another not only new method, not only new process, not only new telescope, we need new method also. One method that I proposed 1 decade ago, that is called polarization, which is getting now much importance for not only for detecting planet, but also for characterizing planet. Since I'm running out of time, so I'm not going through it. Now, what I will say that at present day technology, it is not possible to take the transmission spectra of a Earth-like planet orbiting around the sun. But in future, very near future, within this decade, we are going to get a few outstanding next generation telescope. Now, you know, Hubble Space Telescope is already functioning for a long time with discovery of so many astronomical objects, unveiling so many mysteries. Spitzer has returned, and it has helped in discovering several molecules in several planets. Kepler has discovered more than 3,000 planets. TESS is already functioning and searching for planet. And next year, James Webb Space Telescope, which is 3 times more powerful than Hubble Space Telescope, will be launched. Then there will be WFIRST, and there will be a dedicated telescope which will only look for molecular signature per planet. And I'm a collaborator of, I'm one of the collaborator of this aerial mission led by Professor Giovanna Tinetti of University College London. At the same time, when we get quite a few outstanding and large space telescope, we are going to get some very big next generation ground-based telescope. One is the European extra large telescope, which will be of 42 meter in diameter. At present in India, we have the largest telescope whose mirror's diameter is only 3.6 meter. That is in Devastal. That is called Devastal Optical Telescope. It is only 3.6 meter. The largest telescope in the world is the Keck telescope, which has a diameter of its reflector 10 meter. This telescope, European extra large telescope, will have a mirror that whose radius or whose diameter will be 42 meter. The same time, we will have a 30-meter telescope, and we, the Indian astronomers, are collaborating with the 30-meter telescope project, and we will be sharing the night of this 30-meter telescope. At the same time, another telescope is coming, that is called the Giant Magellanic Telescope, which is 24 meter, whose diameter of the reflector. These two telescopes, the ELT and the GMT, will be pushed in Chile, whereas TMT will be in the northern hemisphere in the Hawaii. So we hope that with the help of this next generation telescope, we will be able within this decade, by the end of this decade, to answer the eternal question if anybody out there or if we are alone, or at least we can tell that if an intelligent life exists or not. So before we discover intelligent life, let us return to our own planet, let us return to ground, and let us look our own pale blue dot. That is the only place that we know till date habitable. That's Earth, that's home, the third planet of an ordinary star called the Sun. An extremely rare combination of astronomical and geological coincidences enabled the life to origin, survive, and evolve on it. From a distance of about 10 million kilometers, the Earth looks like a blue marble. As we move further and further, the planet appears as a pale blue dot floating in the vast emptiness of space. So special, yet so vulnerable. So crowded, yet so lonely. So common, yet so unique. So insignificant, yet so great. A mote of dust suspended in a beam of sunlight. Now, believe it or not, accept it or not, so far we have only one place, that is the Earth. Nowhere we have got any signal or any signature which can tell that there is another planet which is very similar to Earth and we can survive. But the space is a dangerous place, and this great planet, this rare planet blessed by life, is exposed to several cosmic danger. So the collision by a comet or a giant asteroid may destroy irreversibly the atmosphere of the Earth, or even it can change the tilt of the Earth axis that controls the seasonal change. And although this is very rare, but we know that 60 million years ago, during the Jurassic epoch, such type of comet collided on the Earth, and that causes the extinction of almost all the ground-based life, including the dinosaur. And if a supernova or if a star explodes within 10 light year or 15 light year near us, then also the amount of ultraviolet ray, gamma ray, all those radiation may destroy the chemistry of the chemical composition of the Earth atmosphere, and life will be completely extinct because the atmosphere will become poisonous. And the gamma ray, the most energetic gamma ray burst that is caused by the collision of two neutron stars, if one happens in our galaxy, then the energy may completely destroy the chemical composition of our Earth. It can causes the mutation in our cell. Usually the sun is a very gentle star, normal star, but nobody knows that it becomes suddenly due to some unknown reason, it emits a giant flare. It may destroy the magnetic field of the Earth that is protecting us, and Earth atmosphere may be completely damaged. Although there could be terrestrial problem, there could be super earthquake, there could be super tsunami, or there could be super volcanoes. Although this astronomical and terrestrial hazard, the probability of this hazard are very less, very tiny, and we don't see anything happening in our nearby, in our neighborhood that may give rise to this danger. But the imminent threat to the Earth, to this planet, is man-made disaster. If an accidental nuclear or chemical biological wear takes place, then the Earth atmosphere will become completely radioactive. The atmosphere will become poisonous, and it will become irreversibly uninhabitable, and life can never origin and survive again. At the same time, the expansion of civilization, the need for energy, the emission of carbon dioxide is making the Earth warmer and warmer. At this rate, it may happen that the Earth may go a runaway greenhouse effect. Similarly, what happened in Venus atmosphere, Earth will become extremely warm. The ozone layer may get a hole. The carbon silicon cycle may get completely destroyed. And at the same time, the groundwater may be all dried up. Therefore, while searching for new planet, while searching for habitable planet, while searching for life beyond our own planet, what we learn the most essential lesson, the greatest lesson, that we need to protect our own planet for a long time. We have to promise, we have to resolve to protect this planet so that generation of children to come can keep on smiling. So let us save the earth and save life. Thank you.
Thank you. Thank you very much, Professor Sujan Sengupta, for a fantastic talk. I mean, not only you spoke of course, the interesting exploration, exciting exploration of exoplanets, the life or their intelligence, not just life, but also an intelligent life and so on, but also technically taking us through the kind of machines and missions that we have, both ground-based and as well as the space missions. But what is also striking and very, very nice, the way you ended, is the need today to save our home, our precious home, I would say, or Mother Earth. And it's very nice and very inspiring and very interesting way to end such a nice, otherwise, a kind of a proper science talk, but also ending with such a nice message.
Thank you, Satta. My apologies for exceeding the time slightly. Now, all my talks, all the things, except that neutrino aspect, is mentioned in my book called Worlds Beyond Our Own, The Search for Habitable Planet, which is published by Spinger. I have given a part of, in my talk, I have given a part of this book. If people are more interested, if they want to know more about planet and its search, they should go, they should collect this book and they should go through this book. Thank you. I'm now unsharing it.
Yeah, sure. Yeah. So I kind of forgot. It was a nice way that you made a connection between the neutrinos used for communication and then the way the rest of the talk. So it's very interesting. So let me take a few questions. So people in the participants in the Zoom call, of course, you can ask directly. You can unmute yourself and ask a question. So let me just ask you a couple of questions from Zoom.
Yeah.
So, from YouTube. There's one question, actually is a long one, from Shailesh Pincha. The question is the transit method. If planets' revolving time is of several decades, we may observe brightness changes of the star only once during operation of telescope. So how can we verify if the brightness change was actually due to a planet or some other object in path, like a comet and so on?
No, the thing is that the transit method or even the radial velocity method can detect only those planets which are nearby. That is, which are within two times the distance between the sun and the Earth. That is called 1 AU. So at the maximum, at present thing, we can measure only up to 1.5 AU for the transit. For radial velocity, it is much less. So what the present telescope capacity, even if we make a bigger telescope capacity, it will be so tiny that because of the technologically constant, not the limitation, even if we make the largest telescope, we cannot detect the reduction in the brightness of the star if the planet is far away, like it is in the place of Pluto or beyond that. So these methods, whatever method we are using, there is another method called gravitational microlensing, through which we can determine a planet which are far away, but not through the transit method or through the radial velocity method. Now, I didn't go through the to describe the gravitational microlensing method. Gravitational microlensing method is actually the application of Einstein general relativity, through which the light bends. So when a star and a nearby star with a planet, they comes into the line of the observer, the brightness of the further the background star increases because of the lens star, nearby star, and it increases again if there is a planet. So this is independent of the distance of the lens star. So the planet which are far distant from their star can be discovered only by gravitational microlensing method, not by the transit method or by the radial velocity method. But at present, we are trying to search for planets which are similar to Earth. So our main aim is to find out planet within 1 AU distance away from a solar type of star. But most of the habitable planet in fainter star are very near to their star. So as the star become fainter and fainter, their habitable zone has to be nearer to nearer, and in that case, transit method will be very effective, because the transit method becomes much easier if the planet is larger and if the planet is nearer to the star.
Yeah. Thanks for that. And another question from the same participant is, say, Earth did not start as a habitable planet, but it actually changed with time. So therefore, can we predict that other planets may also become habitable in future, or were habitable in the past according to their present atmosphere? So,
see, the thing is that, yeah, we know that the Earth was molten. The moon was not there. The moon appeared after 50 million years of the Earth was born. All those things are there. But we cannot, our main aim is to find the biosignature. So why should we go to a planet which will become habitable, which may not become also habitable? See, it is not necessarily the habitable planet can habitate. Many other conditions are also needed, like the presence of a Jupiter certain type of planet, like the presence of a magnetic field, like the presence of a big satellite like moon, which is monitoring, which stabilizes the motion, the orbital motion of Earth. There are earthquakes, there are volcanoes, many things are needed for the Earth to become really habitating. Even it may be in habitable zone. So if a planet today is not in the habitable zone, we do not want to waste our time to see that when it will come to the habitable. So our aim is to discover as many rocky planets as possible in the habitable zone of a normal star or a main sequence star, and then look for biosignature, that if already life exists there or not. But we do not go for a speculation that this planet may one day will become habitable, or one day intelligent life. So this life evolution is also probabilistic case. The life doesn't mean that always in other planet, even if life origins and it evolves, it's not necessarily that it will go to intelligent life. See, the human species, the present form of the human species has appeared just 200,000 years ago, whereas the first form of life appeared here 4 billion years ago. So it's a probabilistic case. When at the time when dinosaurs exist, that time there was no Homo sapiens, nothing was there. And now the dinosaur got extinct and it has never appeared when the human being is there. So the evolution by the natural selection is also very probabilistic, and it's very peculiar. It doesn't lead to intelligent online life. By the way, even the Earth, the other life can survive if there is no human being. So we are looking for both unintelligent and intelligent life, even in the form of amoeba or one cell, if they affect the atmosphere, and we can see those effects in the atmosphere of this planet, so that we can infer that there may be some biological activity going on. After that, we can make our future discoveries or future investigation.
Okay, thanks for that. There are a couple of more questions on the on the Zoom, but there's one question at least I want to take from YouTube. This is maybe, I mean, if you can answer this, Vandana Manchanda, sir, how much energy is there in the whole universe? I mean, so this little probably out of your kind of the topic today, but if you want to answer it in a way.
In fact, not only in my talk, how much energy, I also don't know.
Okay.
I don't think anybody knows how much energy
is there,
because that is when the Big Bang produced all the things at that time. So some energies are hidden, some energy are visible. Yes. So we can't say that how much energy is in the whole universe.
Whole universe, yeah. Okay. Nevertheless, let us come back. There are a couple of more questions, quick questions maybe you can answer in Zoom. This is from Syed Masood Ali. Thank you very much for your great talk. Will you please briefly tell about the polarization method you suggested? I think you skipped that slide. Maybe a couple of minutes if you can kind of spend on that.
I can again go and I will play if you allow some time, at least 4 minutes time, 3 or 4 minutes time.
Okay, sir. Yeah.
Okay.
Yeah.
Okay, let me share the screen again. Now, please watch this video that explains the polarization. This is made by my collaborator in JPL and Caltech. After we discovered polarization and band-like structure from the nearest brown dwarf called Lumen 16b. So I was one of the collaborator, and this is the method that I first proposed in 2001. It was confirmed for brown dwarf in 2002. And now being applied to exoplanets.
What is polarization? Technically speaking, polarization is the measure of the anisotropy of a radiation field. Light is a wave of electric and magnetic fields. These waves can be oriented in any direction. The direction of each wave's oscillation is called its polarization. Most light sources, including natural light, produce randomly oriented waves. We call that light unpolarized. However, if the light waves are in the same direction, we say they are polarized. A device called a polarizer lets us measure light polarization. A polarizer allows light of the matching orientation to pass. It blocks light of the opposite orientation. Unpolarized light will pass through the polarizer at any orientation. Now, how does light become polarized? Light becomes polarized either by the presence of a magnetic field or when light scatters off of a surface. A properly oriented polarizer can block this reflected light. Light can also become polarized from scattering off of gas and dust particles in an atmosphere. You can see this effect in the sky by rotating your head while wearing polarized sunglasses. The amount of light that gets polarized tells us about the gas and particle properties in the atmosphere. Polarization studies have helped us understand the atmosphere of the other planets in the solar system. The unpolarized star light becomes polarized when it scatters of high altitude haze or cloud in the atmosphere. However, if the atmosphere is uniform, the cloud is distributed homogeneously, or if the object is perfectly spherical, then the net polarization becomes zero as the polarization in all directions cancel out. But if the cloud is distributed inhomogeneously in band-like structure, or if the object is oblate because of its rotation on its own axis, like our Jupiter, Saturn, or Earth, then the net polarization becomes non-zero. On the other hand, if a planet transits across a star or a satellite or exomoon transit a planet, then also the net polarization can be non-zero.
So in 2016, in one paper, me and my collaborator Mark Marley proposed how a exomoon can be also detected through polarization. Before that, we worked on detailed model of polarization from planets and from brown dwarf, but it was first suggested by me in 2001, and it was confirmed for brown dwarf, that is the eldest brother of the planet, which are neither planet nor star, in subsequently in 2002 itself. So now the JPL team, the Caltech team, they are in collaboration, of course, with me, are extensively working on polarization and trying to find out polarized light from planets.
Okay, thank you very much for that nice explanation of about polarization. We have one last question from Dr. Suresh Kumar. This is concerning your communication through neutrino. The question is, neutrino beam can be collimated, but can it be focused like in optics? So for detectable neutrino signal, what should be the flux of at transmission?
Well, so see, the thing is that if it is sent by the intelligent life, we do not know it. They will definitely not know that we have a India-based neutrino observatory in Tamil Nadu or a ice cube observatory. So it may pass, but if the area passes through the Earth, so what is the estimation is that if there is a few TeV muon collider produces this collimated, it can produce, we can receive 7 to 9 neutrino event per year, and that is much higher than any natural source of neutrinos. So the thing is that neutrino can be also used, they can also send the neutrino in a very periodic way, and thus giving the signal that it is come in the artificial. The advantage is that the radio wave, they comes from different, there's a large number of objects in the universe, from almost everything, even from planet to quasar, radio wave comes, and they come sometime in periodic way, sometimes they come in a radio burst way, all type of things. So it is very difficult to distinguish a artificial signal, a coded signal in radio. But in neutrino, that cannot be. The number of sources that produces neutrinos are not that high, which can be received by us, and the event rate, that will also tell us, and the periodicity of the event will also tell us that it is not the background radiation.
So thank you very much with that. I think it's fantastic talk and very engaging in the sense, it also led to nice discussion about the concepts that you mentioned. So thank you very much on behalf of all the participants, Prof. Sengupta. And with that, we come to the end of this lecture.
Hello, sir. I have one question, sorry.
Yeah, we are actually running a bit late. Okay, can you please quickly ask the question?
Yeah. My question is regarding the magnetic field of our Earth. So the main thing why our Earth is habitable is because of the magnetic field, which kind of protects the radiation from our own sun and other radiation around in the galaxies. So is it possible that we can detect somehow the magnetic field from other exoplanets? Because our Earth has around, I think, 0.5 Gauss. So is it possible to have any space instrument, something which can be stationed somewhere outside and detect magnetic field from other exoplanets or something like that?
So the thing is that what you have heard is right, but your information is incomplete and wrong. The thing is that, first of all, this the magnetic field protects the charged particle to entering, not the radiation. And the Earth magnetic field is a dipolar. Now all the solar planet has magnetic field. Okay. So this Earth magnetic field has been produced because of the circulation of some molten iron inside it, and so that gives rise to the dynamo effect. Even in Jupiter, there are the strongest magnetic field is there. In Saturn also magnetic field is there. Now, because of Earth magnetic field, the charged particle from the energetic charged particle or the flare that is in plasma form, it cannot penetrate the Earth atmosphere, but it penetrates through the magnetic pole, giving rise to the aurora borealis. Now, yes, so we know one thing is that the interaction of the magnetic field between Jupiter and Europa gives rise to radio wave. So if the presence of magnetic field cannot be measured directly because they will be faint that they are far, far away. But if somehow they are strong enough to produce radio wave from the planet, then we can detect it. But having said that, it is not so easy thing, because here we are living inside the solar system. We can separate the Jupiter, the location of the Jupiter, Saturn, Earth, and the Sun. But in an exoplanet system, if we get a radio wave, we cannot make out that whether it is coming from the star or it is coming from the planet. So that's the difficult thing. But yes, there are some reports recently for the discovery of radio emission or radio burst from some planet, which are attributed to the presence of magnetic field of the planets. But personally, I am not very sure that whether the origin of those radio wave is the planet itself or it is the star, because the star may have something different property because of which this radio. So it is the problem of distinguishing the magnetic field or the effect of magnetic field from the star to the planet.
Okay.
Thank you, sir.
Thank you very much. Thank you, everybody. So with that, we come to the end of today's lecture. So we'll join again next Monday. But until then, take care. And also, let me wish on behalf of the INO project and all of us, I hope the new year will be much better than what we have gone through, and enjoy your life.
Thank you, Satta. Thank you very much, and wish you also a very happy New Year. And to all the India-based Neutrino Observatory members, my New Year's greetings to everybody. Thank you.
Thank you, sir. Thank you very much. Take care, sir.